Hello everyone, welcome to my video of my walkthrough of question 10 of the MAS1 Spring 2019 exam. You are given the following information about two gamblers. The two gamblers start with a total fortune of 100 tokens between them. They plan to go to two different and independent casinos to try their luck. Each gambler has a 50% chance of winning one token and a 50% chance of losing one token at each play. All plays are mutually independent. The gamblers initially divide their 100 combined tokens to maximize the probability that both of their fortunes will eventually reach 100 tokens. Calculate the product of their initial fortunes in tokens. For this problem, there's a pretty quick and easy formula that you can have memorized to make this question pretty easy, and that is the probability of ruin is 1 minus the starting chip count divided by the ending or stopping condition chip count. So for example, if you started with 25 tokens and you were going to play until you lost them all or got to 100, your probability of ruin would be 1 minus 25 over 100, which would be 75%. So that's how this equation works in the event that you're pretty much playing with these exact conditions of this problem where it's just a fair coin flip. However, I wanted to dig into where this equation comes from and really the more generic, when it isn't a 50-50 game, it's an unfair game. And that really stems from when I was studying for FM. I just want to give a shout out to Mancinelli's Math Lab. This is a great YouTube channel if you're studying for PRFM. Highly recommend it. Definitely use a lot of his videos for FM, and that was kind of the inspiration to me starting to make these videos for MAS1. So just wanted to have that one quick shout out, but going back to this problem and what we're looking at, wanted to derive where this formula is actually coming from. And so this whole section, none of this you need to know for the MAS1 exam itself, but I just wanted to kind of work through and understand how it came to be. So first, I wanted to include my initial attempt that actually ends up not working, which was thinking of this as a Markov transition matrix and seeing if we can calculate that stable state. So you know that x, so where are you currently times the transition matrix equals itself, and if you can find that, that's the long run probabilities. So if you have 0 coins, you're stuck there. You're never going to magically have more coins, so that's why there's just a 1 for this row. If you have 0, you're stuck in 0. And then same thing at the end. If you have 100, you're stuck at 100 because you've won the game. Otherwise, you have your failure and success rates, so I have those here specified by F and S, and so you can either, wherever you are on the diagonal, so in this case if you have 1 coin, you have a chance of F of going to 0 coins or a chance of S of going to 2 coins, and you follow that along. Multiply these all out, try to calculate something, and it just didn't work out. So not sure why I'm sharing this, but just thought I'd let you know I tried to give it an honest go on my own, and didn't work out, mainly because you don't get a system of equations that you can easily solve. So now to actually derive it, I'm going to include the links at the end that I ended up reading up on this derivation, but if you've ever taken diff-EQ, differential equations, apparently this is difference equations, so it's the same thing for discrete case. I could be totally wrong, I never took differential equations, but apparently that's kind of what we're doing here, just in a discrete case. So in order to get this derivation, we want to know, given a starting number of tokens I, so you know we know that each gambler in the problem is going to start with some number between 1 and 100, or 0 and 100. However many tokens they start with, what is the probability that that gambler is going to reach his goal number of tokens? We can break that into two parts. We can say, well, that's the same as if you started at I, that's the same as taking the probability of losing your very first round. So that L, that's the probability you lose a round, multiplied by the probability of winning the overall game, but where you then have one less token. Right? So if I want to know what's the probability I win everything given I start with 50 tokens, well, that's the same as saying the probability I lose a round, which in this case is 50%, multiplied by the probability of winning everything if I start with 49 tokens, plus the probability of, well, what if I win, so that's that other 50%, but then multiplied by the probability of winning the overall game if I were to start with 51 tokens. So that's all that's going on here, and this is why it's a difference equation. It's a series based off of time, or not really time in this case, it's the amount of tokens you have. And then the other thing to define here is that L plus W equals 1. You either win or lose a round. What we can then do is multiply P subscript I by 1, where 1 we choose to write it as L plus W. We then can get like terms on each side, so let's see, P to the I. So I take W P to the I plus 1, and then subtract the W P subscript I. That's how I get the left side here. Then the right side is L times P subscript I, subtract L times P subscript I minus 1. I then divide both sides by W, and I get this equation. So this is one of those cases where all the steps of the math kind of make sense. I don't know how someone got to this point and thought, okay, let's leave it here. My gut reaction was to try to solve for something, but we want to leave this in terms of P subscript I plus 1 minus P subscript I equals this equation on the right. So what we can do is we consider I equals 1 as a base case. And so when we plug in I equals 1, we get P subscript 2 minus P subscript 1 equals the probability of losing a round divided by winning a round, multiplied by P subscript 1 minus P subscript 0. And what's special about this is if you have 0 tokens, the probability you're going to win the entire game is 0. You've already run out of tokens, it's hopeless at that point. And so we can actually substitute in for P subscript 0 the value of 0. So at this point we get P subscript 2 minus P subscript 1 equals the loss rate divided by the win rate multiplied by P subscript 1. We then can just go to the next case, so consider I equals 2. And here we get this equation. But what's neat about this is on the right side we have P subscript 2 minus P subscript 1, which we actually just solved for. It's right here. So we know that that quantity equals L over W times P subscript 1. So all we have to do is substitute that in here, and we get this quantity. And so what you'll see is we're just adding in a L over W factor on the right. So when I was 1, it was L over W to the power of 1. When I is 2, it's L over W to the power of 2. Likewise, we can plug in I equals 3. The exact same thing happens. On the right, we get the quantity that we saw for in the previous I. Plug that in, and then we just multiply by a factor of L under W, L over W. So this isn't a formal proof, but I'm forgetting the term. Inductive proof, but you can kind of see what's going on. We're just multiplying by that common factor. So then this is only the case for the non-extremes. So likewise, for 0, we knew that the probability was 0 of winning if you have no tokens. If we have n, I equal to n, then we know that we have won the game, so the probability is 100. So we're just dealing with the cases in between where this quantity equals L over W to the power of I multiplied by P subscript 1. So now that we've done that, and we've gotten this equation, we can then take the summation of all those terms, and I kind of have the reasoning here. So Ideally, we would like to just have p subscript I or just p subscript I plus 1 or something like that. So the way we can do that is by summing from 1 to k for all these i's. And that gets us almost there. We're still left with a p subscript 1, but that's far easier to deal with. So the reason why this works is if we actually start at the top, we have k plus 1 minus k, and then we add k minus 1, so that's going to be k minus 1 plus 1 is just k here, and then this is going to be k minus 1. And so when it started at k, that minus term is going to cancel out with the positive term for k minus 1. And so all the terms just cancel all the way down to the bottom, so all you're left with is the very first, or the largest value, which is k, the left portion, and then the smallest value, which is I equal 1, is going to be left in the right portion. And that's why all you're left with is p subscript k plus 1 minus p subscript 1. So then what we can do is say, and all I did here was switch the sides, so that's why it's mixed up here. So moving the right side to the left, and then what's inside the summation, we've solved for that, right? That's L over W to the power of I times P subscript 1. And then what you can do is add P subscript 1 to both sides. So we're going to cancel that out, so that way we're just left with P subscript K plus 1. And then on the right, what that does is we can actually ignore this term here and instead start our summation at 0. Because when you plug in I equals 0, this L over W to the power of 0 is 1, and all you're left with is that P subscript 1. So that's why this term just kind of disappears, but what's changing from here to here is this starting condition is at 0, not 1. And then just to make things more obvious, I pulled this constant out to the left. At this point, we then remember our high school math class where we learned this property. I had forgotten it, but I'll add a link for the derivation of this as well in the description of the video if you're interested. But when you have the summation of a rate, a subscript I, where it is ranging between 0 and 1, or I believe, it works out to be this formula. P subscript k plus 1 equals, we can then, we have this constant pulled out, and then we just plug in L over W for our A term here. And that's how we get this formula. Then what we can finally do is recognize that we just have k plus 1 and k plus 1. So before there was k and k plus 1, but since we only have that one term, we can just rewrite it as k instead of k plus 1. So this is just me simplifying the notation. Now, all we have to do is find out what p subscript 1 equals. And we can do that by taking this formula and using our knowledge that we know that once you have all the tokens, you win. So p subscript n equals 1. We know that fact. And so plugging n for k here, so when we use subscript n, we know the probability is 1. And so we set this whole formula to 1. And then we can solve for p subscript 1, so that's just going to flip the denominator and the numerator. And finally we have our constant p subscript 1. Then, going back to this equation, we're going to plug in what we found p subscript 1 equals into this equation, and that's what we have here. And then we see some terms cancel, so the numerator on the left, denominator on the right cancel. And then finally we are left with the probability of winning a game when you start with k tokens is equal to this formula, where L is the probability of losing a round and W is the probability of winning a round. And then if we want ruin, we can just do 1 minus that quantity. So, at this point, this is actually a formula that pops up on other MAS1 past exams. I'm not sure if it's in spring 2019 or not, but this is a formula you need to know. Um, so even though that's not going to be relevant to this specific problem, this is definitely something that needs to be memorized. And again, this is just probability of ruin for an unfair game. Now in terms of this problem, it's a toss-up, and if you do 50-50, you'll see 50 over 50 is 1, to the power of something is 1, and then 1 minus that is 0, and so you're dividing by 0, so that doesn't work. So again, needed to look up some past knowledge I used to have, and what you do here is apply L'Hopital's rule. So given a bunch of conditions, we're able to use it, and so we're just taking the derivative of the numerator and denominator separately, and that ratio is k over n. So using L'Hopital's rule, you can say that their original function's f over g is also k over n. So as the limit approaches loss over w equaling 1, you approach this final solution. So that was a mouthful. That's why there's a large gap between videos posting. This took me a while to figure out. This Columbia paper is where most of this came from. So if you wanted to look at that source material, that's where I got most of this from. I also found a YouTube video, which was a Harvard lecture that talked through some of this as well, if you would prefer someone smarter than myself talking you through these equations. I then also have that geometric series derivation, as well as some comments on L'Hopital's rule, if you'd like to look up that as well. So that concludes the derivation portion of this video. Again, this is not something you're going to ever need to do on the fly. Really, if you have this formula memorized, you should be good for the exam. And then if you forgot the probability of ruin for a fair game, you could, worst case scenario, plug in values really close to 0.5 and say like, oh, you win 50.0001% of the time and lose 49.999% of the time. And that would be a good worst case scenario. So just make sure you know this formula for the exam. So going back to the original question, we want to know how much should each of the two gamblers start with such that their total number of starting tokens is 100, and we want to maximize the probability that they both achieve 100 tokens themselves independently. So really, I feel like this is a question that you can just kind of intuit that you're pretty much one of them's screwed if they start with only one token. So what you want to achieve is a balance between the two of them, and so that results in each of them starting with 50 tokens, and then the product of their starting 50 times 50 is just 2,500. This ends up being correct, but assuming you don't have that intuition, or you do and you want to just double check, because that's definitely not the safest way to answer these questions, what we can instead do is use the formula that we had for probability of ruin is 1 minus the starting tokens divided by the ending condition number of tokens. And then in terms of study materials, they talk about ruin a lot, but it's funny, this question actually cares what's the probability they both win. And so we need to do 1 minus that 1 minus value. So all you're left with is the starting number of tokens divided by the ending condition. So what we can do here is, what's the probability of both them winning? Well, they're independent. They go to different casinos and it's totally independent, so we can just multiply those probabilities. One of them is going to start with X number of tokens, however many that is, divided by 100, and then the other person is going to have what's left over. So they have 100 tokens total, so that's this 100, and then subtract whatever the other person starts with. So if one person started with 10 coins, the other person is going to start with 100 minus 10, or 90 coins of the 100. So this product is the probability of them both winning, and that works out to be this on the right. So you get x over 100 times 100 divided by 100 is just x over 100, and then x over 100 times negative x over 100 is negative x squared over 10,000. So now that we have this, we want to maximize that value. So what selection of x is going to maximize the probability? So when you want to maximize something, you take the derivative with respect to that thing and then set it equal to 0. So here we get x over 100 just becomes 1 over 100, and then minus x squared over 10,000 is just going to become negative 2x over 10,000, and all of that equals 0. Solving for x results in 50, so our intuition was correct. So when both of them start with 50 coins, that maximizes the probability they both win. I will add that technically we aren't done yet, because it's possible this is a local minimum, so it might be the case that this is the absolute worst case starting condition. But given that there aren't multiple roots, and none of the answer selections are like a solution does not exist, you can just kind of stop at this point. The one exception to that is if you want to check edge cases. So that's something that's not going to show up in these maximum calculations when you're setting derivatives equal to 0. Maybe the min value of 0 or the max value of 100 are the actual maximums within your range. And while that can happen in some problems, for this problem we know that's not occurring, because if either of them start with 0 tokens, we know right off the bat that they lose. So since we know that's the case, and this is the only root we get, we actually don't even need to bother checking the second derivative to see if it's a maximum versus a minimum. So since our solution is 50, the question asks for the product of their starting conditions. So one starts with 50, the other starts with 50. Their product is 2,500, and that gets us our answer of E. Wow, you made it through a 20-minute video for one question. That's impressive. If you found your way to the end of this video, thanks for watching, and please consider subscribing for future videos. Thanks. Bye.